Hi, everyone. Today we are going to be talking about standing waves on a string. So this is a ukulele. I don't play the ukulele, just so you know, but I have one. Um, and all musical instruments make their sound because of when you pluck it, you send a vibration through the string, and that causes a standing wave on a string. Okay, so what is a standing wave? We're going to talk about that today. So, in your notes, we are going to start this on page 16. Okay. So, standing waves require three components. Okay. And those three components are reflection, interference, and resonance. Okay. So these three things, we haven't really talked about these three things in detail with you being home, but when a wave is sent, so I'm going to talk about reflection really quick. When a pulse is sent on a string, let's say, and there's a fixed boundary on the other side, when that pulse gets to that boundary, what happens is it gets inverted. Okay. By a fixed boundary, I mean like there's something on the other side of it. Like it's not a loose string, it's just something on the other side of it. Okay. So it's important to know that when it gets reflected, it comes back upside down. Okay. And that keeps happening. And then these always come back. The reflection is always inverted. Okay. Interference, we briefly talked about that in one of the videos. That means that when two waves are on top of each other, they either cancel each other out with destructive interference, or if they're on top of each other, they kind of enhance each other by adding up the amplitudes. So this is constructive interference. Okay. And resonance is, in my opinion, the most important thing here, because if we have a natural frequency of an object, such as, let's say, a swing at a playground, when you pump your legs, you have to catch that exact vibration of that swing. Okay. Like you can't just pump your legs randomly. So you have to kind of get into the rhythm of that swing. And when you're able to do that with resonance, your amplitude of the swing gets higher and higher. So when we talk about a swing or a pendulum, the amplitude is how high it gets from one side to another. Okay. So when we talk about resonance, if we are able to match that natural frequency of the swing, it's resonating. Okay. And you hear sometimes, maybe you hear people say stuff like, oh, that idea really resonates with me. What that means is, I totally get it. I feel you, because what you're saying matches exactly how I feel. So resonance is basically matching the natural frequency of something. Okay. Um, so we're going to talk about what a standing wave is. So I have a video that I'm going to show you through this screen. And I wish I could do this at home and demonstrate, but I don't have something that would make this type of shape. I was thinking about going to the building and getting a slinky to show you, but a standing wave is basically when one person sends a wave and it bounces off the partner. So this has to do with, if I pluck the string, I would have a standing wave, or if in this video you see a standing wave too. And what it means is, it looks like, if you like kind of squint your eyes, you can see it look like a wave that's not moving. Okay, now these guys are going pretty slow. Okay, now you see this, and this is a standing wave. You see kind of like, if you squint your eyes and if you like see it really quickly, it looks like it's a wave that's just standing. We're going to draw pictures of this. Okay, so I'll post this video on my website as well, but I'm going to start with the notes here. Okay, so frequencies of standing waves. Frequencies must fit the string length, okay? So the first way to think about a standing wave is when you have this type of shape, okay? This wave was sent over to the other side, and then it was reflected backwards, okay? So in that video I just showed you, there was a person standing here, another person standing here. You had this type of shape. What I see is one crest and then a trough right underneath that. This is the reflection though. So really when we think about how much of a wavelength we see, we're talking about just this part right here in red. Okay. Now I don't want you to get confused to think that a standing wave is caused by people all of the time. Really what we're talking about is you see this type of thing on instruments, okay, like string instruments specifically. So when you pluck something, there's a wave that's sent over to the other side and then it gets reflected back, okay? So this bubble shape, what I call here, is called an antinode, okay? An antinode. And an antinode is basically when you have constructive interference in a standing wave, okay? So this area, it looks like this because this is all constructive interference. So when we talk about this, the first harmonic, this is the first harmonic, and the reason why it's called the first harmonic is because this is the smallest possibility of a standing wave you can have on a string. So there's only one antinode here, okay? These points right here, the ends, are what we call nodes. So in the first harmonic, we have two nodes. And a node is basically when you have destructive interference. I can't spell interference. Interference. Okay, so that's when the waves cancel each other out, and that's when you have basically nothing there. Again, this is the first harmonic, so we're going to leave it at that. So what I see here is I see if this was one wavelength, okay, and what I see is this and part of the reflection. This is one wavelength. So how many wavelengths do you see right here with the first harmonic? And basically that is this right here. So if this from this point to this point is one wavelength, this is half a wavelength. Okay, so we're going to say the length of this string and the first harmonic is half a wavelength. Okay, so we're going to go through all these harmonics and you'll see a pattern without a problem, I think. Okay. Okay, so for this, I see one antinode and a second antinode. Okay, so two antinodes. And then I'm going to do this in yellow. This right here is a node, this right here is a node, and this right here is a node. It's like where the wave is pinched. Okay, so I see three nodes. And we'll talk about what F1, F2, F3, F4, F5 is. Okay, so because this is basically what I drew here, and I'll redraw this just so in case you missed it the first time and that was confusing. If I send a wave like this, there's a reflection. So I'm gonna do my reflection in my dash line. Okay, what I see here, this entire thing is one wavelength. And you know it's one wavelength because after this point, it would start repeating itself. So this is one wavelength. Okay, so it's as if a person was standing here, sending a pulse to another person standing here, and they get that exactly like in the video I just clicked on. So this would be the second harmonic, and this length of this string would be equal to the size of one wavelength. You write one wavelength. Okay, so I'm just going to write wavelength like that. Okay. So if this frequency was some frequency F1, I'm just going to call it F1, and we knew what that frequency is. F2 would be 2 times F1. Okay. The first harmonic is called the fundamental frequency. Okay. That's the first harmonic for everything. So your second frequency, your second harmonic frequency would be 2 times the fundamental. Okay. So we're going to go through the third harmonic. So if, I'm going to blow this up a little bit. If this was one wavelength, I have half more here. So for the third harmonic, I have 1.5 wavelengths, or 3 halves of a wavelength. Okay, because 2 antinodes make 1 wavelength, so I have 3 antinodes, so that's 1.5 wavelengths. So I have 3 antinodes, and how many nodes do I have? 1, 2, 3, 4. Okay, and to find this frequency, I would take 3 times the fundamental. And the pattern keeps going on and on and on forever. So in this case, I have 4 antinodes, 5 nodes. That's 1, 2, 3, 4, 5. And my frequency would be 4 times my fundamental. And my length of the string, so now this string is being able to cause more than 1 wavelength. I see 2 wavelengths here. Okay, so I'm going to write 2 wavelengths, but I'm going to keep everything in fractions because I want you to see a pattern that way. So instead of writing 2 lambda, I'm going to write 4 over 2 lambda. Okay, so I want you to pause the video and figure out what the 5th harmonic would look like if I had to draw the antinodes. Okay, basically fill out this entire part once you pause the video. Okay, I'm assuming you paused the video and you did that. So for the 5th harmonic, I have 5 antinodes. Okay, so how am I going to draw 5 antinodes? Everyone has a tough time drawing this for the first time. Okay, that's 5 antinodes, and I have 6 nodes, 6 little spots right here. Again, nodes are where it's destructive interference. F5 would be 5 times the fundamental, and this would be 5 halves lambda. Okay, that's the 5th harmonic. Okay, so we're going to go to the next page. So if you could figure out an equation for this, what would it be? Well, L, let's go back actually so we can talk about this. I want you to note that for the 3rd harmonic, Where do you see the number 3 here? Well, I see it right here in the numerator of the fraction. For the fourth harmonic, it says forced. Where do you see the number 4 here? Right here in the numerator, and so on. So that value is consistent for standing waves on a string. So my equation would be L equals n over 2 times lambda, where n is an integer, first of all, and the value of the harmonic. Okay. So if I rearrange that and solve for lambda, what I would do, I'm going to do this over here. If L equals n over 2 times lambda, and I rearrange that and solve for lambda, I'm going to multiply each side by 2 and divide each side by n. So sometimes you'll have to solve for lambda, and you would get 2L over n. Okay, so what about the frequencies? Well, if I know this equation, this is the first equation we talked about in this unit. Okay, so I'm going to rearrange this, and I'm going to say, instead of solving for V, I'm going to solve for F. F equals V over lambda. Okay, and I'm going to put an n next to it because n represents the frequency of that nth harmonic. Okay, so I'm going to put an n right next to this. And what I'm going to write here is V over, instead of lambda n, I'm going to plug in this equation, 2L over n, and that simplifies to NV over 2L. Okay, and understand that L is the length of the string. And of course, that's in meters. Lambda is the wavelength. And that's also in meters. N is the number of harmonics that we're on. Okay, and V, now what we're talking about is the speed of the wave. Just like we're talking about when we described it in the very beginning. Okay, so here is your equation for frequency of that harmonic. So I'm going to rewrite that just so you have it organized. Fn equals NV over 2L. Okay. Also, if I wanted to find the frequency of any harmonic, if I knew the fundamental, if you go back to that page, it's really easy to understand what that is. So if I knew the fundamental, I'm going to take the harmonic that I'm on, which in this case is 2, and multiply that by the fundamental. Okay, so what I can say here is the frequency of that harmonic equals that number times the fundamental. Okay, so what does that look like when we start doing problems? So here are your examples. This is also in your notes. If the frequency of the 7th harmonic is 2100 hertz of a vibrating string, what is the frequency of the first harmonic and the second harmonic? Okay, so I'm going to write down my knowns and my unknowns. My n is 7, and that frequency of the 7th harmonic is 2100 hertz. I'm looking for the first harmonic and the second harmonic. Okay, so I'm going to use obviously this equation. So F7, which is 2100 hertz, equals 7 times F1. Okay, so I'm going to do some math, mental math, I hope, and that's going to give me a fundamental frequency of 300 hertz. Okay, but how do I find F2? Well, F2 would be 2 that's n, times my fundamental. I'm still using this equation right here, times 300 hertz. And that gives me 600 hertz. Okay. Okay. So number 2. Number 1 would be like a really basic question. Number 2 is when it gets a little bit more, we get to use some of the bigger equations. Okay. So I'm going to draw pictures for all of these because if you're a visual learner, if you think about this in terms of what the diagram looks like, it's going to help you a lot. So a standing wave is formed on a stretched string that is 10 meters long. What are the wavelengths for the first harmonic and the fourth harmonic? Okay, here's a standing wave, and this is what the first harmonic looks like. Okay, so this entire string is 10 meters long. Ask yourself, how much of a wavelength do you see here? Okay, so if this was an entire wavelength, it would look something like this, right? So how much of a wavelength do you see? Well, this is only half. So if it was an entire wavelength, it would go from this point to this point, and that wavelength would be double of 10, which is 20 meters. Okay, well, let's say you really hate drawing stuff, which I don't know why you would do that. But anyway, 10 meters. If I want to use the equation, I'm going to go find my L equation, and I have this equation right here. L equals n over 2 lambda. Actually, I'm going to use this equation because I'm solving for lambda. So lambda equals 2L over n. So L equals, lambda equals 2L over n. So I'm plugging it in. 2 times L, which is the length of the string, which is 10 meters, over 1, because I'm on the first harmonic. This is the first harmonic. So I'm just going to do my math, and I get 20 meters still, which is what I got. Okay, so now for the fourth harmonic, here's your string. Your string has not changed. It's still 10 meters, but I'm on the fourth harmonic. So what that looks like is something like this. Okay, and how many wavelengths do you see here? Well, I see 1 right there, and then 2. Again, we're not counting the reflection. So that's like on top of it, so it doesn't matter. We're not counting that. So if I see 2 wavelengths and this entire string is 10, well, 1 wavelength would go from this point to this point. That's obviously half. So what's half of L? It's going to be 5 meters. Or we're going to plug it in. 2 times my length of the string over n. What's n in this case? It's the fourth harmonic, so that's 4. So 20 meters over 4 equals 5 meters. And that's what I got right here. Okay. So let's see if there's anything else I need to talk about. That wraps up my lecture. Let's see, I just want to make sure I got everything. Okay, so we're going to stop right there, and I will talk to you later. Bye.